work with a null hypothesis. Sometimes you see it written that way. And your null hypothesis is typically that the mean of the two populations are equal to one another. Okay, that they're equal. In other words, there's no difference between group A and group B. And what you're trying to do is you're trying to prove an alternative hypothesis, typically which is the mean of group 1 does not equal the mean of group 2. Sometimes the way that you'll see this written is mu1 minus mu2 equals 0, and mu1 minus mu2 does not equal 0, right? Really, these two are really pretty much, you're saying the same thing in either way that you phrase this. Okay, mathematically, you'll see a lot of statisticians. Yeah, you'll see a lot of public health people do it this way because it just kind of makes sense that way. Statisticians, mathematical statisticians might do it this way because that 0, it gets involved in a formula that we wind up kind of dropping out a factor because of present of that 0. But if you look at the textbook and you look at some of the formulas, you'll see why mathematically they phrase it that way sometimes. But either way is okay. Okay, so now what we're doing here is we're going to say that these two things are equal unless we prove with 95% certainty. In other words, an alpha error of 0.05 or less, that if we reject this null hypothesis and say that the means really are different for the two populations, that we're only going to be wrong less than 5% of the time. Okay, so that's really what we're after. That's our null hypothesis. That's our alternative hypothesis. Now, let's start to apply this in a few places. Okay, one of the things that comes up quite a bit is the idea of one-sided versus two-sided. Okay, so now, let's say that I have a null hypothesis where I say that, for instance, drug A, I'm testing drug A versus drug B, versus a placebo. Okay, so my null hypothesis is going to be mu1 is equal to mu2. And my alternative hypothesis, let's say that this is a blood pressure drug. My alternative hypothesis is going to be that mu1 does not equal mu2, right? That's my null hypothesis. That's my alternative hypothesis. Okay, and I'm going to say my alpha error, I'm willing to accept an error of 0.05. Let's take a look at the distribution of possible sample results I might get here. Okay, here's the difference in the blood pressure, let's say. Here's my possible distribution. And I'm looking for the probability, and the two blood pressures have to be far enough apart, averages, that there's less than 5% chance of getting a result in these two that's the same. So if I just define my alternative hypothesis this way, it doesn't prejudge whether the blood pressure in group A is lower or higher than group B. So I don't know. It could be that if this is group A, that I'm comparing it to a population B, the placebo, that could be higher result or could be a lower result. So my 5% chance of error, when I phrase the alternative hypothesis this way, my 5% chance of error has to be split up into two sides, 2.5% that side, 2.5% that side. So we know our T-score or our Z-score has to be pretty far out to get to that point. Well, now, what if I had phrased it instead? I had phrased it, drug A, the way that it works is a vasodilator. Okay, or it relaxes your veins or arteries. Right, it's a vasodilator, and the way that it works, it's not possible for this to increase blood pressure. It can only reduce blood pressure. So it's physically impossible. I want to only examine the possibility that mu1 is less than mu2. Now when I look at that distribution, right, I can say to myself, whoops, that's not very clear. When I look at that distribution, I'm a little off here, I'm holding it sideways. When I look at that distribution, I'm only looking at the possibility that this is the mean for group A, that the mean for group B is that side of 5%. I can put all 5% on this side. So now, since that's 5%, you know the z-score, the t-score that you need in order to reject the null hypothesis is going to be a smaller number. Okay, like the z-score would be like 1.64 instead of 1.96, because you can put all you legalized by phrasing it this way, putting all of this possible error on one side. Of course, you got to really, really be sure that that's the case before you do a one-sided test like this. Okay, almost all of the time you will be doing a two-sided test, because you really need to be able to justify a one-sided test if you want to do it. Okay, so that's the difference between a one-sided test and a two-sided test. Okay, and so if I said mu1 for alternative hypothesis, if I said mu1 minus mu2 is greater than 0, that's also a one-sided test, right? Because normally my alternative hypothesis would be does not equal 0, right? So you can phrase it a lot of ways, but you get the idea that when you do a one-sided test, you're kind of doing a little bit of a cheat to prove it, because you're putting all of your possible error on the fact that the second group has to be either bigger or bigger or smaller, not bigger or bigger and smaller. Could be either way for a two-sided test. Okay, so again, usually you're doing a two-sided test. Okay, so now let's put all this stuff that we just talked about to work. Single-sided t-tests. Okay, so now let's take a look. I'm going to open up an Excel file. Let's see. Okay, here's an Excel file. We've looked at this one before, I think, but it's a pretty useful one. I'm going to make this a little smaller here, and then I'm going to pop it open here, zoom in a little bit. Let's see if we can't get away with this size. Okay. And all these numbers in here at the same time. There we go. Okay, so there's 20 numbers here, right? We have the label at the top, elapsed time. This is maybe the average amount of time for a chemical reaction to take place, and and if it's dependent on, or a biological reaction to take place, or a test result to take place, and we want to know if this test is faster than another or something like that. But these values, in this case, the way I described it, could be seconds, could be a lot of other things if we did it, if we phrase this a different way, if we phrase the study a different way. But we're going to analyze it the same way. In this case, we're going to compare this to a known population. We're going to compare it to a population where it's known that the average is 65. Okay, and we know that average is 65. So now, at this point, we have a single sample. We don't know what the average for this population is in column A. We do know what the average for the population, the other population in column C is. It's 65. That's given to us. Okay, now at this stage, in a particular problem, they might tell you that the standard deviation for the population here is a certain value. If that's the case, and you assume that the variability for this population and for this population are the same, you can use that sigma so that you can go ahead and use a z-table to calculate your probabilities here. Okay, so I'm going to do this both ways. If you don't know sigma, where are you going to get your standard deviation for your test? Where you're going to have to get it from these numbers right here. So I'm going to go ahead and I'm going to calculate the mean here. Okay, and that's going to be equal to average, parentheses, parentheses. I'm going to take all these numbers, find the average of them. It's equal to 59.3. I'm going to take the standard deviation of this population. That's equal to STDEV parentheses, and I'm going to take standard deviation of this. Okay, enter, and it's 9.8. Okay, so now I want to compare this mean of 59.3, which is from a sample, so I don't know really what the population it is, to a known population value of 65, single sample t-test. So we know I'm going to go over here and do this on my paper now. Okay, and I'm going to cheat. You're not allowed to cheat. I'm going to cheat to save time. You're not allowed to do this cheat on the exam, however. Let me try and narrow this over so I can get both in here at the same time. Okay, I'm going to cheat and I'm going to say that my X bar is 60. It was really 59.7. And my standard deviation is equal to 10. Okay, that's my little cheat. You can't use that cheat, but I can use that cheat. And I'm comparing it to a mean that's equal to, what was it again, 65. Okay, so I want to compare these two. So I look at my X bar and my standard deviation. One way I could look at this is I could do my confidence interval here, couldn't I? I could say, well, standard deviation is 10. The standard error for a sample size, what was the sample size again? It was 20, right? Standard error for this is going to be equal to standard deviation over the square root of 20, right? Square root of 20 is, let me open this up anyway because it's going to come in handy. Square root of 20 is 4.47. I'm going to call it 4.5. Okay, is 10 divided by 4.5, and 10 divided by 4.5 is equal to 2.22222. I'm going to just call that 2. Okay, I'm going to call this 2.2. Okay, again, I'm cheating. You can't cheat. The only time you can round off is at the very end of your calculation. So now I could do a confidence interval here. I could say that my confidence interval is X bar plus or minus my, in this case, I'm going to have to use what? A t-score or a z-score? I need an opinion from you guys so I know you're there and you're not sleeping. T-score or z-score here? Okay, I've got one z-score. Go ahead, keep going. Anybody else? Any other opinions? Okay, how can you justify using a z-score there? Do you know the standard deviation of this population? We don't know. Well, hang on a second. How did I calculate the standard deviation? I calculated the standard deviation from my sample. I don't know the standard deviation of the population, right? That wasn't given for that population or for this population. I calculated the standard deviation based on 20 values, right? So I have to use a t-score there, right? I can't use that. I got to use a t-score for my 95% confidence interval. Okay, so everybody get that? Get why I'm saying that? Well, no, actually, what you would be assuming, I understand because we say that a lot, don't we? We say, I'm going to assume it's the same as as this other population, or the two groups have the same standard deviation. Well, if we had known the population standard deviation here, right, like right in there, if that had been filled in and we knew it, and then we said, I'm going to assume it's the same for our experimental group where we took these readings, right? I can understand you making that leap, right? But we don't know it. So our only source of the standard deviation for this was from this group of 20 people that we sampled. Okay. Now, had this group been bigger than 30, then we would have said, well, even though we don't know the population standard deviation for group A, right, and we're not making any assumptions about it being the same as for group C, right, then I'm going to use the z-score because it's such a big sample that I feel it's going to be close. The difference between the z-score and the t-score for that value is not going to make that much difference. But in this case, it's smaller than 30 sample size, so I got to use t. Had I used z, this would have been 1.96. Okay, so it's plus or minus t times the standard error, okay, which we said was 2.2. So x bar is 60 plus or minus, well, I need the t-score now for this, don't I? Okay, and I'm going to go over here and I'm going to look it up. And this is the same t-table you have in your book. Okay, here's our t-table. Whoops. Here's our z-table also. We'll need that later. Okay, here's our t-table. Okay, and for a 95% confidence interval, 0.025 to 2.5% up both tails. This one's the right tail, so you double it for the left tail. And a sample size of 20, but this is degrees of freedom here, not sample size, so it's 19. I'm going to go across here, and I'm going to use 2.9. 2.9. In your example, you're going to use 2.903 until you're done. But I'm going to use 2.1. I'm going to round that off to 2.1, make my calculation easier. Right? So again, I get to cheat, you don't. So this is 2.1 times my standard error, which is 2.2. So that comes out to 2.1 times 2.2 equals 4.62. I'm going to store that in my memory here. And let's see, then I'm going to take 60, and I'm going to subtract that from there. And it gives me 55.38, 55.4. And I'm going to clear that, and I'm going to put in 60 again. And this time I'm going to add my standard error. Okay, let's see. Standard error is going to be here. So now I get 64.6. Okay, that's my 95% confidence interval. Well, I know that the population mean for that other group is 65, right? So I know that my mean for my experimental group is between, for the true population that my experimental group came from, is between 55.4 and 64.6. So I am 95% certain that this mean is going to be different than this population mean. Okay, so I can reject my null hypothesis that group A, the mean for group A and the mean for group B are the same. Okay, so in that case, I reject my null hypothesis. I'm sorry I didn't start with a null and alternative hypothesis. The other way I can do this is by doing a t-test. Okay, and in the t-test, we're actually going to take these two means, x bar minus mu over the standard error. And we're going to calculate a t-score for that value. Okay, and what's that going to be? It's going to be equal to 60 minus 65, okay, divided by the standard error, which we calculated here, which was 2.2. Okay, and that's going to be equal to, let's see what that comes out to, 5 over 2.2 is equal to, 5 divided by 2.2 is equal to 2.227. 2.227. Right, was that? Let's see what I got there. 2.27. Okay, that's what my t-score is for the difference between these two means. These two means are 2.27 standard errors apart for a sample size of 20, okay, or degrees of freedom 19. Okay, well now, if I go to my t-table and I go down here again to 19 and I go to 95% certainty or 5% chance of being wrong, my alpha error is 5%, I see a value of 2.09. I know that now I can use that value as my critical value for t. T critical for a sample size of 20, in other words, degrees of freedom equal 19, is equal to 2.09. In other words, if I get a t-value that exceeds that, it's less than 5% chance that these two means came from the same population. So I can reject my null hypothesis. That's the way I would use my confidence interval to solve this problem. And that's the way that I would use a t-test, a single sample t-test to solve this problem. Okay, so the t-test, in fact, a little bit easier to use in this case, isn't it? Okay, so now, you guys comfortable with that? Make some sense. Okay, I'm going to do this one more time. Yeah, t-score is negative, right? Yes. Okay, but when we do a two-sided test, right? When we do a two-sided test, the t-score that I would be using for this would be minus 2.09. I'd be looking at the other side. In other words, it really doesn't matter which way you do this because you're really looking for the in a two-sided test. You're looking for the magnitude of that t value. Okay, but you're absolutely right. It would have been a negative number, and I would have been comparing it to is the absolute value of it bigger than negative 2.09? In other words, or rather, is it smaller on the other side than is it further away from the mean from zero, and that's on that side of the distribution, but from zero t-score on that side of the distribution. Okay, but you're right.